Okay, by now we have learned quite a bit about magnetic resonance, and I want to recap the essentials as we know them so far. We have a nuclear equilibrium magnetization M0 that develops. If you enter a magnet, your nuclei in your body will develop a nuclear equilibrium magnetization. This magnetization is given by the difference in the number of spins in the upper and lower energy level, the difference between the two times their magnetic moment. Now I'll rewrite this equation here, so we'll write it in this form, and we'll have now n1 over n2, where we can use the Boltzmann distribution. So n1 over n2, the Boltzmann distribution has been used here. And now what we will do is, we will use the linearization, because we have said delta E over kt is very small, so e to the minus x can be approximated by 1 minus x if x is very small compared to 1. And then with this linearization of the equation, we have the magnetization is given by this term here, and then I'll substitute the delta E with the term that we have seen previously, and this is now the nuclear magnetization, macroscopic equilibrium magnetization that we have. Now we'll substitute for the fact that N2 is essentially half of all the spins. This is to a very good approximation true, and then we obtain this expression here. So the magnetization is given by some constants of the system. Boltzmann constant, temperature we can assume is constant, Boltzmann constant, Planck's constant, the dipole moment, and then we have gyromagnetic ratio, B0, and the number of spins. So this is the resulting relationship. And I stress here, it is good to understand this relationship, some dependencies here. And we have the magnetization here is increases with the following terms. The number of spins. So that is essentially the number of molecules. If we increase n, then then the magnetization increases. If we increase the magnetic field, then the magnetization increases. That's this term here, B0. If we increase the gyromagnetic ratio gamma, then the magnetization, the thermodynamic equilibrium magnetization increases. So taking all this together, for magnetic resonance imaging, which nucleus is the most favorable to look at? Now if we look at these three values here, we can control experimentally only one, that's the magnetic field. That's produced by the magnet that we construct. The number of spins is given by the organ under investigation, the gyromagnetic ratio by the nucleus. So we need to find a nucleus with a high gyromagnetic ratio and a high number of spins. And so this is essentially the hydrogen nucleus, H1, it's the proton, has the highest gamma as we have seen before, and water is highly concentrated. Whether we like it or not, we are 80%, typically 80% of our body is water. So for MRI, we are mainly focusing on hydrogen, imaging the hydrogen atom in water. Okay, so we'll take the Larmor equation here, and here I want to introduce the term that we have. From this we can glean the Larmor frequency, which is given by gamma B0 2 pi. That's in hertz, so it's a frequency. If we take angular velocity in radian per second, then the omega L, the Larmor frequency, is gamma B0. This we have to bear in mind. Now one thing that is non-negotiable in magnetic resonance is a convention about the reference system, the coordinate system. The static magnetic field B0 that we generate with our magnet, it's that magnet, the magnetic field generated by our scanner. That magnetic field is by definition always along Z. We do not negotiate this convention. It is fixed. So Z is always along the magnetic field, it's along Z. Then we have the equilibrium magnetization is also along Z. The thermodynamic equilibrium magnetization is always parallel along Z. And I want to give credit here to Ed Purcell, who discovered magnetic resonance nuclear magnetic resonance and received the Nobel Prize for Physics in 1952. Now, quantum mechanics will tell you that the spin will never align with the magnetic field. There's always a transverse component. However, the thermodynamic equilibrium magnetization is always along Z and does not have a transverse component. And in the appendix that we provide as a PDF on this course, the explanation is provided by the random phase approximation of equilibrium magnetization. So why there is no net transverse component of the magnetization at thermodynamic equilibrium. Now, we need a magnet to generate a magnetic field that's along Z. This results in a separation of the spins in upper and lower energy level, which creates an equilibrium, thermodynamic equilibrium magnetization, M0. We'll call the main magnetic field always B0, and we'll call the equilibrium magnetization always M0. Now, if we look at the energy difference here, the delta E, we find it is actually very small. And if you calculate this, you'll find that this is on the order of micro electron volts. So there's one consequence. We are using non-ionizing electromagnetic fields for magnetic resonance. So that's good. That is different from the X-ray techniques. But given that this term here depends on the magnitude of the delta E here, this enters linearly. So as we increase the energy difference between the energy levels, we increase the magnetization. There's also a consequence. It is insensitive. So the following statement is certainly true. MR is safe, magnetic resonance is safe. We're dealing with non-ionizing radiation, but it is insensitive. We cannot imagine to do an MR experiment with concentrations on the order of picomolar. There are just not enough molecules there to produce a measurable magnetic nuclear magnetization that we can reasonably detect in the body. So therefore, we would ideally like to increase the sensitivity. And how can we do that? We've seen just on the previous slide that the equilibrium magnetization depends on the number of factors that are given by the nucleus and some universal constants. And temperature, of course, which is more or less also given. So the only parameter that is open for manipulation is the external magnetic field B0. And here's an example of comparing a scan of the lower abdomen at 0.2 Tesla and 1.5 Tesla. If you look here, the image is grainy and it gets much sharper here at 1.5 Tesla. If we take the spine here, we have again 0.2 Tesla here, grainy image, we see very nice details, but a very crisp image at 1.5 Tesla. So comparing the image, the sensitivity at lower field and higher field, we notice a clear improvement in sensitivity. Here's another example that is brain function. It's functional imaging. We'll discuss that in lecture 12. This is a comparison of 1.5 with 4 Tesla. Clearly, the sensitivity increases substantially with higher magnetic field. Here we have an example of MRI of the breast. This is a standard MRI. We're seeing something here that is suspicious. It's a bit clearer here, but this is a breast image, a standard breast image, and here's a breast image with a fat signal removed. We'll discuss that in 2 weeks, how this is removed. And then one can see clearly at 3 Tesla here compared to 1.5 Tesla. One can clearly see the potentially neoplastic lesion here because the signal is not related to fat. So clearly an improvement in specificity with the higher magnetic field. Now, one thing that we need to remember for this course, this week, and so on, the theoretically maximum possible MR signal is dictated by the equilibrium nuclear magnetization M0. This is a given of the system. We cannot go beyond that. So any mechanism to generate contrast results in a reduction in magnetization. We'll discuss in the weeks to come how this happens. So we are limited by the thermodynamic equilibrium nuclear magnetization M0 in our sensitivity. Gives us a maximum signal that is possible.